Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to Gauss law and electric field due to various charge configurations. So in this video, we are going to discuss about the electric field due to a uniformly charged sphere. Okay, so we know the basic statement of Gauss law, which states that the electric flux because of any charge configuration is 1 by epsilon 0 times the net charge enclosed by a closed surface which encompasses the whole charge configuration. So that is called as Gauss law, and that surface, that imaginary surface, that is called as the Gaussian surface. So Q net by epsilon 0, that's one way of expressing it. So the second way is through the closed surface integration of the electric field vector and the area element, the surface element vector. So here the situation is that we have a uniformly charged sphere. Okay, it is positively charged. It has a radius capital R, and the total charge because of this sphere is Q, and it has a volume charge density of rho. Okay, volume charge density rho. Okay, this. So we know that the volume charge density is equal to the total charge by total volume, which is the volume of the sphere, let's say. Okay, so volume of sphere we know of any particular radius, that is equal to 4 by 3 pi, here the radius is capital R, so 4 by 3 pi r cube. So the charge in terms of the volume charge density can be expressed as 4 by 3 pi r cube into rho. This is the expression of charge in terms of the volume charge density, the total charge enclosed by it. So here there are four situations in which we have to determine or calculate the electric field, the expression of electric field. First situation is at a certain distance away or outside the charged sphere. Here small r here, which is outside at this point, which is outside the sphere. Okay, then we have to calculate on the surface of the sphere, and then inside the sphere, then at the center. So this is the center O. So first let us consider this case, outside the sphere. So we pick a point P outside the sphere, which is at a distance small r from center O. So taking this point P and the distance between P and O as the radius, we draw an imaginary sphere, which is the Gaussian surface in this case, the spherical Gaussian surface. It encloses this charged sphere having total charge Q. Now we know that according to the rule, electric flux phi E is equal to the closed surface integration of the electric field vector and the area element vector, which is the dot product of the electric field vector and the area element vector. Now if we consider this small area here at the point P, then the area element vector is directed radially outwards, normally outwards, perpendicularly outwards away from it, and we know that the electric field vectors are always directed away from the positive charge. Okay, they are always directed away from the positive charge. So this is the positive charge. So the electric field vector, this is the electric field vector. So here both the electric field vector and the area element vector, the surface element vector, they are in the same direction. They are in the same direction throughout the sphere. Okay, they are in the same direction. So the angle between them is 0 degree. So here if we solve it, it becomes E vector magnitude ds vector magnitude cos 0 degree, which is equal to closed surface integration of E ds. Now another important thing is that as all the points on this spherical Gaussian surface, any number of points, infinite number of points that are present on this Gaussian surface, they are at a fixed distance small r from the center, okay, or they are at fixed distance from the charged sphere for every point, okay, they are at fixed distance. So it means the electric field is constant. So the electric field will be constant as the distance is constant, the separation gap is constant, so electric field will also be constant. So this will become, E will go outside the integration, this will become ds. Now area of a sphere, we know it is equal to E into 4 pi r square. The radius is small r, 4 pi r square. So this is electric flux. But we also know that electric flux as per Gauss law is equal to Q net by epsilon 0. Q net is the total charge enclosed by the Gaussian surface. Here the total charge enclosed by the Gaussian surface is how much? That is equal to Q, small q. This much amount of charge is enclosed by the Gaussian surface. It is inside the Gaussian surface, this charged sphere. Okay, this charged sphere, the total charge of this uniformly charged sphere is Q. So here Q net is equal to Q. So this becomes E into 4 pi r square is equal to how much? Q by epsilon 0. That implies E is equal to Q by 4 pi epsilon 0 small r square. This is outside the sphere. Outside the sphere. When the separation distance small r is greater than the radius of the charged sphere, that is capital R. This is outside the sphere. This is what we have derived here. E is equal to Q by 4 pi epsilon 0 small r square outside the sphere, where the distance r is greater than the radius of the sphere, the charged sphere. The radius, distance from the center is greater than the radius of the charged sphere, capital R. Next is on the surface, okay, on the surface. So that is also the same situation. So suppose we consider a situation again where we pick a point on the surface, let's say here, okay, here we pick a point P dash here. So here also the same situation. Here at a certain distance away, the area is in the same direction, the electric field also in the same direction, E vector, the angle between them is 0, theta is equal to 0 degree, and the same situations will be repeated again. That is phi E is equal to closed surface integration of E vector dot ds vector equal to E ds cos 0 degree, which is equal to E ds. As the Gaussian surface is a fixed radius, the distance is, the separation gap is fixed, So it will be, E will be constant, so it will become E vector ds. Now in this case, the distance or the separation gap, that is equal to, nearly equal to capital R. Okay, just we are taking the Gaussian surface, just very close to the charge sphere, almost touching, like this, almost touching. This will be the Gaussian surface. Okay, so here this radius will be nearly equal to capital R. So the charge enclosed by the Gaussian surface here also will be Q, this much. This much charge will be enclosed by this Gaussian surface for electric field calculation on the surface of the sphere. So here it will be what? R will be nearly equal to capital R. So this will become E into 4 pi capital R square, because the surface area of a sphere is equal to 4 pi R square. So this is the electric flux. Now we also know, as per Gauss law, that this flux is equal to Q net by epsilon 0. Again, the charge enclosed is equal to Q. So this becomes Q by epsilon 0. That implies E is equal to Q by 4 pi epsilon 0 capital R square. Okay, in the previous case it was Q by 4 pi epsilon 0 small r square, the general expression. Here, as R is nearly equal to capital R, the separation gap is nearly equal to capital R, so this is the expression. Now we have already previously determined that this Q is equal to, the total charge on the sphere is equal to 4 by 3 pi capital RQ into rho. Rho is the volume charge density. So if we substitute this here, okay, if we substitute this here, okay, where it is gone now? Okay, here if we substitute this Q with 4 by 3 pi RQ rho, let's see what happens. So we have calculated E is equal to Q by 4 pi epsilon 0 capital R square. Okay, so if we substitute Q with 4 by 3 pi capital R cube rho, then it will become electric field is equal to 4 by 3 pi R cube rho by 4 pi epsilon 0 R square. 4 gets cancelled, pi gets cancelled, R square, here R cube, we are left with R. So this becomes rho, that is the volume charge density, radius of the charge sphere, by 3 epsilon 0. This is the electric field on the surface of the sphere. This. So on the surface of the sphere, the electric field is equal to this, rho r by 3 epsilon 0 on the surface of the sphere. Okay. So next we have to determine the electric field inside the sphere. So here we pick a point inside the sphere. Okay, here this point, okay, we have picked it inside the sphere, which is at a distance small r from the center O. Capital R is the radius of the entire positive charge sphere, and the small r is the distance of the point P inside the sphere from the center O. Okay, so we have to determine the electric field at this point. So any point on this this circular sphere, if we take small r as the radius and draw a sphere, any point on this spherical surface, okay, Gaussian surface, at any point the electric field vector and the area element vector, they will be in the same direction, okay, same direction. Again, the same reason, area element vector is always directed radially outwards, and the electric field is also always directed away from a positive charge, so they will always be in the same direction for anything, okay. Here also ds vector, here electric field, they will be in the same direction, so the angle between them will be 0 always, as they're in the same direction. So here, as the sphere is not hollow, okay, it is not hollow, it is solid sphere, so this much portion, okay, this radius r portion, okay, this which with the volume 4 by 3 pi r cube, this much volume of the sphere will contribute to the electric charge, okay, it will contribute to the electric charge. So we know that volume charge density rho is equal to q by volume, that implies q is equal to rho v. So in this case, the charge contributed by this inner sphere q dash is equal to portion or volume of the sphere involved, that is 4 by 3 pi r cube, into the volume charge density rho, this, okay, this, okay. Now we have already determined that rho is equal to how much? Here rho is equal to, that is equal to q by 4 by 3 pi r cube, okay, q by 4 by 3 pi r cube, that is the volume charge density. So here q dash will be equal to okay, q dash will be equal to 4 by 3 pi r cube, that is pi small r cube, into rho, which is equal to q by 4 by 3 pi capital R cube, where the entire volume of the sphere is considered. Here only the portion of the sphere which is involved, that is inside region of the sphere, that is considered, the small radius r, which is lesser than the radius of the sphere. Here the entire radius, the entire charge contributed by the sphere, that is considered. So this becomes 4 by 3, 4 by 3 gets cancelled, pi gets cancelled, so this becomes q dash, that is the charge enclosed by the Gaussian surface, that is equal to q small r cube by capital R cube, okay. So this much charge is contributed by the inner sphere of radius r, which is lesser than capital R, okay, this. Now again, electric flux phi E is equal to closed surface integration of the dot product of electric field vector and the surface element area vector, so equal to closed surface integration of E ds cos 0 degree, as the angle between E vector and ds vector is 0 degree always. So this becomes closed surface integration of E ds. Now again, in this inner region, in this inner sphere, okay, let's use a different clean diagram. In this inner sphere, all the points, okay, all the points in this inner sphere there are fixed distance small r from the center. Okay, they are at a fixed distance, so that means the electric field will also be constant. Okay, electric field will be constant, so this E will go outside, so this becomes E closed surface integration ds. Now surface area of a sphere, that is equal to 4 pi r square. So here the inner sphere has radius small r, so this becomes E into 4 pi small r square, so which is equal to the charge enclosed by the Gaussian surface, which is equal to q dash by epsilon 0. Why here we have not written q? Because q is for the entire sphere, capital R. Okay, 4 by 3 pi capital R cube into rho, that is equal to q. Q dash is equal to 4 by 3 pi small r cube into rho. R is lesser than the radius of the sphere, the inner sphere, this inner sphere of radius small r. Okay, so q dash by epsilon 0. So q dash is equal to, we have already calculated, q dash is how much? Q small r cube by capital R cube. So this becomes q small r cube by capital R cube into epsilon 0. Now again, q is how much? 4 by 3 pi r cube rho, this 4 by 3 pi r cube rho. So if we substitute that here, it will become, let me use a different clean slide. So here we have E into 4 pi small r square is equal to q small r cube by epsilon 0 capital R cube, according to this. E into 4 pi r square is q r cube by epsilon 0 r cube. Here in place of q we will substitute 4 by 3 pi capital R cube into rho. Okay, here in place of this q we will substitute, that implies E into 4 pi r square is equal to 4 by 3 pi capital R cube rho small r cube by epsilon 0 capital R cube. Here let's use a different ink. Okay, capital R cube gets cancelled. Okay, here pi 4 then r square, here we have r, we are left with this. So we can write E is equal to rho small r by, here we are left with 3, so 3 goes to the denominator, 3 epsilon 0. Okay, this is the electric field inside the sphere. Okay, inside the sphere. So we had already calculated electric field on the surface of the sphere, which was how much? Rho capital R by 3 epsilon 0 on the surface of the sphere. Inside the sphere, at a certain distance small r from the center, it is rho small r by 3 epsilon 0. Okay, inside the sphere it is rho r by 3 epsilon 0, rho r by 3 epsilon 0. So here it is, we can change it, rho small r by 3 epsilon 0, that is inside the sphere. Inside the sphere. Now another interesting thing, at the center of the sphere, at the center of the sphere, if you want to calculate the electric field, at the center of the sphere, r, small r will be equal to 0. At the center of the sphere, the small r will be equal to 0 at the center. So, if you substitute the small r with 0, electric field will be equal to 0 at the center of the sphere. At the center of the sphere. This. So, here we have calculated the electric field due to a uniformly charged sphere with 4 cases. In the first case, outside the sphere at a certain distance, small r, outside where r is greater than the radius of the sphere. In that case, we got this q by 4 pi epsilon 0 small r square. Then we calculated the electric field on the surface of the sphere, which we got rho capital R by 3 epsilon 0. Okay, this. Then we calculated the electric field inside the sphere. So there we got E is equal to rho R by 3 epsilon 0. So if you see, for r, or the distance or the separation lesser than the radius of the sphere, electric field is directly proportional to the separation gap. And for r, the separation gap between the center and the point where we want to determine the electric field, when that is greater than the radius of the sphere, it is inversely proportional to the square of the separation distance, as it is equal to q by 4 pi epsilon 0 r square. This, it is inversely proportional to the square of the separation distance. So if we try to draw a plot between electric field and the separation distance, it will be something like this. Suppose we draw a plot where we have, this is the separation distance from the center and this is the electric field. This is capital R, okay, point where R is equal to capital R. So up to this point, electric field is proportional to it, so it goes on increasing. Then beyond, this is R lesser than R, this region up to this point. Then beyond this, R lesser than R, sorry, this is R greater than R, sorry, this is R greater than R, I'm sorry, this is R greater than R, small r greater than capital R. So here it is inversely proportional to the square of the separation distance, so it decreases parabolically. Okay, this, here it is in this region, E is directly proportional to R, here E is inversely proportional to the square of the separation distance. So small r lesser than the radius of the sphere, here the separation distance is greater than the radius of the sphere. Okay, so here we have done. So let us try to understand this whole situation first. So here we have a uniformly charged sphere, okay, a uniformly charged sphere with this positively charged sphere throughout. Now this is the center O and it has a radius r, okay, this, and it has a linear charge density, a volume charge density of rho. Okay, volume charge density. Now, the three situations which we have is we have to determine the electric field at any point outside the surface of the sphere. So for that we have to pick a Gaussian surface like this, where the distance of the center and that point P, OP, is equal to small r, which is greater than the radius of the sphere. Okay, so as it is a solid sphere, okay, as it is a solid sphere, so the entire volume of the sphere will contribute to the charge. Okay, the entire volume of the sphere will contribute to the charge. Then in the second case, what we have to do for the same thing, for the same situation, okay, let's copy it here. Okay, here we have to determine the electric field on the surface. Okay, just on the surface here. Okay, on the surface. So here we have to pick a Gaussian surface which is very close to the surface of the sphere. Okay, where the distance of this Gaussian surface from the center, that is r, is nearly equal to capital R. Okay, this is the second condition where we have to calculate the electric field on the surface. Here also the entire charge Q, because of the entire volume 4 by 3 pi r cube, that will come into play. The entire volume, the entire charge Q. Okay. Now we have a different situation, okay, where we are considering, okay, we are considering a portion inside the sphere, okay, a region inside the sphere. Let's say this is the center and we consider this much portion of the sphere. So let me try to, make it more clear. Suppose we divide it into two cross sections. So this is the inside of the sphere, okay, this is the inside of the sphere. So we are considering only this much portion. This is the center, only this much portion, volume 4 by 3 pi small r cube. So here, because of this much volume, only charge Q dash will come into play, where Q dash is equal to the volume or the portion of the volume of the inner sphere 4 by 3 pi small r cube, where r is lesser than the radius of the entire sphere, into the volume charge density. Okay, volume charge density rho, which is equal to the total charge divided by the total volume, which is equal to 4 by 3 pi capital R cube. So here only this much portion or this much region of the sphere will contribute to the electronic charge, because the charge is uniformly distributed. Charge is uniformly distributed throughout the sphere, okay, throughout the sphere with volume charge density rho, okay, the volume charge density rho, okay, rho coulomb per meter cube or per centimeter cube or whatever units you can use, whatever units you are using. Okay, so first is the point outside, okay, the point outside the sphere. This is the first case. This is the first case, a point outside the sphere, this, where the entire charge comes into play, the entire volume, the entire charge. This is the second case, where on the surface, okay, a point on the surface. So here the Gaussian surface, this is the Gaussian surface, which has a radius almost equal to the radius of the sphere. Here this is the Gaussian surface which has a radius which is greater than the radius of the sphere. Then the third case is this one, the point which is inside the sphere, okay, a point which is inside the sphere. So the inner sphere with radius r, with r lesser than the radius of the sphere, that is considered. And in this case, this is the Gaussian surface, okay, this is the Gaussian surface, and it has a radius lesser than the radius of the entire sphere. Okay, so this is the whole situation which I have explained in a three-dimensional point of view. So friends, I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.